So we're going to go from Jason's theory about buried weak layers into a case study from last winter, from the December drought layer, or what we've been calling the DDL. And our first presenter who's going to talk about the DDL is Patrick Wright of the Bridger Teton Avalanche Center. And Patrick, he's also co-founder of Inversion Labs, works as a commercial applications programmer with synoptic data, MesoWest. Patrick is smarter than your average bear, okay? So a lot of these things that have happened on the BT website, thank Patrick. Yeah, but he still likes to get out, get on skis, bikes, foot in the mountains as much as possible. So he's got a good balance of theory and practice. And Patrick's going to talk about the theory of our DDL. Here you go, Patrick.
So yeah, thanks very much for inviting me, Lynn. So for those of you who have not seen this photo before, or if you saw it yourselves driving around the valley last spring, this is an avalanche event, a deep, wet slab in Little Tuckerman's Bowl on Teton Pass that's believed to have failed on the DDL, the December drought layer. So this was a major weak layer in our snowpack last season. A lot of you are very familiar with it and probably saw this yourselves when you were driving around. So I'm going to talk more about these spring events in Mount Taylor in particular, and then really try to look at the weak layer that was responsible for these events, the formation and the preservation of that layer. So here's kind of the outline that I'll look at, and I'm going to start with the season overview, go pretty quick through the whole season and look at the weather patterns, really focusing on the fall. And then look at the formation of this weak layer, some of the mechanisms that were at play, and very quickly talk about the preservation of that layer throughout the season and how it was able to persist all the way to the spring to have big, deep events like this. So just starting the beginning of the season, it was really different than this year. We had these giant wildfires near Bondurant. Things were very dry in September. Last year, we had a ton of snow in September, and this is what it looked like in October. Grand Targhee was looking like midwinter in September, so it was really amazing. But moving into November, when we were forming these weak layers, mid-mountain was actually at bare ground by October, and Rendezvous Bowl had 17 inches on the ground. So now I'm going to go into kind of the months of November and December and just step you through the snowpack and what happened with the weather. And I'll move out so I can point better. So this upper panel these are both plots, panels from the Snowpack Tracker tool that we've developed for the Bridger Teton Center. And this upper panel here is snow data. The dark blue bars are new snow totals. The light blue are snow water equivalent, or precipitation, times 10. So, you know, if they're equal height, that indicates about 10% snow density. And the line in the background here is snow depth on the right axis. You can pretty much ignore those yellow bars, that's snowpack settlement. In the lower panel, this is previous 24-hour air temperatures, maximum in red and minimum in blue. So air temps, snow data. And as we step through, we had this big event in the early part of the month with some avalanche activity. We had 4 to 5 feet of settled snow depth on the ground moving into mid-November. And we had great powder skiing in this time zone, and things really changed on the 21st here, when this tropical flow rise. So we had multiple days of rain. This day in particular, over an inch of rain up to 10,500, 11,000 feet. So this really set the stage for the rest of the season. Here's what some rain runnels look like at Togety Pass, 10,000 feet, a couple of days after that. And this is a snow profile from Don Sheriff that I've picked out from Avalanche Bowl. And I put a big red box around here reading the details of your notes, and we'll hold you to your comments here, Don. But many non-shaded aspects sopping wet top to bottom. So that's really stuck out to me. And I know that it wasn't like that everywhere. The rain didn't penetrate the full depth of the snowpack everywhere, but there was a lot of rain, and it soaked a good portion of the snow. You can also see some temperature measurements there indicating that this was isothermal at 0 degrees C. He just measured near the surface, but you can assume this extends down isothermal from that comment. So this was really a 7-day thaw period that ended with record high temperatures on the 26th. And I do want to point out this initial freeze right here. So we had a brief cold period that created this November crust. That was the initial freeze that created the crust. So there's a great picture of right after that small initial freeze of the crust we had. So then we went into this 5-day freeze period. I do want to point out there was these small precip events during that. It got cold, and now we're really starting to freeze that rain and the snow. This ended here, whoops, let me back up. Ended here on the 3rd with this big snow event. So this is the snow that's to become the December drought layer, right? And that kind of leads into the big drought period itself. So what I want to do is take a closer look at these temperatures, because this is really important when we're thinking about the formation of the crust. And you got to go to the 15-minute data to really look at the temperatures and the timing. And you can see this initial freeze was about 48 hours below freezing at the summit, but it was only 18 hours below freezing at mid-mountain. So this was a really initial formation of the crust. There was probably still a lot of heat in the snowpack, liquid water in the grain space, things like that. Then we drop into this period, 5 to 6 days below freezing, depending on elevation. Some snow totals ending with this big dump here. So then we go into a 10-day high-pressure ridge, and this was a very regional high-pressure system that extended up into Canada. Clear skies, cold nights. This is what created our weak layer. This was the drought of the December drought layer, right? And ended kind of data burial, depending on when you call it, with this big snowstorm on the 20th, and then we went into our first major cycle on this weak layer around Christmas. So here's what the snowpack looked like at the end of the Christmas storm on December 30th. And I can put some overlays on there. Here's that rain crust, the December drought layer, and our Christmas storm. So I'm going to do the rest of the season kind of in one fell swoop here, moving through rather quick. And you can see we had 3 major cycles. On the bottom panel now, what I've put in here is avalanche events, where red are deep events, yellow are moderate, and green are small. So these are greater than 44 inch. These are our deep events, which mostly did run on that weak layer, the December drought layer. So this is the February cycle. This was probably the biggest of those 3. We were seeing big crowns like this one in Garnet Canyon. A lot of things in mature timber that were running, the north-facing slopes in Avalanche Canyon, Garnet Canyon, a lot of things were running on this cycle. It was very impressive. So I'm really summarizing this in a broad stroke here, but the rest of the season, low probability, high consequence, going into a period where we still had occasional deep slab events popping off, sometimes on this layer, especially in late February. The problem remaining on the bulletin through early March, but largely the snowpack was bridging loads, the slab was gaining strength. So this is a snow pit I dug on a south-facing slope just below Old Pass Road, and I just want to point out that this is March, very end of March 31st, almost April. This was isothermal all the way through. I didn't plot the temperature, and there was water in the pore space of all the grains, really wet, warm snowpack, but I could still clearly find those facets down at the base and clearly see the crust. So this was really pretty amazing to me how persistent this was being. So we reached our peak snowpack depth on April 13th, and then we had these major events in the spring. So I've put these 3 days here. You can see those events there with their estimated crown depths. And these were our big spring deep wet slab events. You saw that picture of the Little Tux event here. I'm just going to show you some pictures of Taylor that happened on April 28th. Oh, and just to point out, these events are temperature related. So I brought the temperature in here. Right, they're not loading related, and in particular, all of these events, the previous 48-hour minimums overnight were at or above freezing. So that's really what drove these deep wet events. So here's Taylor. This happened on April 28th. Just get a drink of water. So yeah, this is Mount Taylor on April 28th. This was a really impressive event. You can see the nature of the crown here. It had really interesting geometry. But I've got some great photos that were shared with me from Don Sheriff, from Kurt Windberg. And you can see what I really want to point out is the level of the snow on these mature trees and kind of the scour line where the height it reaches in the gully here. So this is coming down into Coal Creek. Really impressive, almost a debris flow with rocks, trees, dirt, lots of water in the flow. Here's the end of the flow coming down into Coal Creek. And I hiked back up here on July 3rd, and this is the snow at that time. This is how much was still remaining. This is really impressive, maybe a half mile from the parking lot. Big trees being taken out on the sides of the gully. And when I told you to kind of keep track of that high scour line, I was standing in the bottom of this trying to imagine how much snow came through, and I think there was a lot of snow that was moving through this gully. And I was just standing in there trying to be like, wow, this is a lot of snow. So again, very mature trees. Someone who knows about aging trees could talk about how historic this event was. And this was that tree that was knocked over. This one is leaning over, and again, that snow you saw in that picture was right up to here, and there I am standing in the summer. So this is all just to motivate drilling in a little deeper with the last half of my talk here about this DDL layer, how it formed, and how it was preserved over the whole season. So drilling in a little deeper, this was a near-surface facet layer, and I've got a picture here, plus surface hoar, by Jay up on the pass of some great surface hoar growth during that drought period. And if we think about the types of near-surface facets, melt layer recrystallization is one that comes to mind right away because we had that rain event. In my mind, this is not really what was happening because the rain layer was totally or mostly frozen when the new snow was deposited. But there definitely was a rain event. There was a crust. So the timing of the freezing when the new snow came is going to be important. And if anyone's familiar with this work, this would be more of a classic dry on wet melt layer recrystallization scenario with a lot of rain and snow being put down on the wet layer directly. So diurnal recrystallization, in my mind, yes, this is the dominant process that we had going on during that drought period. So if we look at diurnal recrystallization closer, this is a figure out of a Carl Birkeland paper where he really tried to define a lot of the terminology for these processes. And it makes sense. I've listed some of these features here that really fit with the formation of our weak layer. The clear cold nights with long wave out radiation dominating, setting up a steep temperature gradient in the near surface. The depth scale made sense for the thickness of our layer over many days, many aspects. And whereas depth hoar can be these much bigger crystal sizes, 4 or 5 millimeters, these were generally the crystal sizes we were seeing as well. So if I kind of overlay some temperature gradients here, I put the rain crust in, the facets, and this is what we're talking about. Some sort of a temperature profile, colder to the left, that gets really cold in the near surface. At night, to the left, and possibly during the day, we've got some sensible heat coming in. Not much radiation because it's December, but we had upper 20s during the days. So this is this bidirectional temperature gradient in the near surface that is resulting in the faceting. And what I want to propose is if we can do something like this, see this arrow here, and bump this temperature gradient over just a little bit, put a line in there like that, we've still got the diurnal swings up here in the near surface, but we've created a steeper gradient overall through the layer just by warming it a little bit. It's still all frozen, but you're just warming that up at the base a little bit. So how do we add heat here? How do we increase the temperature gradient through the DDL? By warming the layers below. And this looks like a complicated equation, but it's really just energy balance in the snowpack. These are all the terms where heat comes into or out of the snowpack. And a big one is rain. And we knew we have a lot of rain. That's a big source of heat into the snow. So the question is, where does all that heat go, and how long does it take to go away? So I think there's a pretty good case that that heat affected our faceting process to some extent. And again, this is Don Sheriff's profile from Avalanche Bowl, where we've got isothermal right after the rain. This is November 30th, and I've kind of cherry-picked these snow profiles, but I think it demonstrates my point pretty well. We actually have 15 centimeters of faceted snow here before that big dump on December 3rd. And you can see the rain crust is knife hard. It's frozen, and it's cooling off. But down here, the snow still at 0 degrees C. So this snowpack's really still trying to cool off. There's probably still liquid water in the grain spaces. And I've just drawn a dash line here to probably what it's like at night, since this was taken during the day. Then you move over mid-drought 2 weeks later, and this kind of cold wedge has been driven much deeper into the snowpack. We're probably getting close to more of a temperature profile that's unaffected by that rain and heat input. So it probably got to this state even much sooner before this, near the beginning of the drought period. But my big question is, how much of an effect did this slow dissipation of heat have on the snow? And just to illustrate this point a little bit better, this is a great example from a Jameson paper, and this is in the British Columbia Mountains. It's a little different because it's dry on wet, but I want to show the time sequence of freezing of this wet layer here with dry on top. And he's got thermistors in the snow that stay there while frontal passage comes through and it gets really cold and the crust freezes. So I'll just walk you through his time increments here. 16 hours, the air temperature dropped to -5. The wet layer is still pinned at 0 C. 21 hours later, the wet layer is still at 0 C. It's probably freezing now, but it hasn't worked through that latent heat of the phase change. And then at 36 hours, it's the rain crust here, these wet grains that are freezing, is actually starting to cool below freezing, dissipating that residual heat. And then at 42 hours later, we're starting to drive this cold down into the snow below. So that's kind of the time scales, and I thought this was a great example of a similar process. So this is my main question: did heat energy from our November rain event elevate temperature at the base of the DDL? And we'd have to answer some of these questions about how deep did the rain penetrate, what was the time scale to dissipate that latent heat, and then the residual heat after that. And did these small precip events before the big snow on December 3rd in the overcast skies kind of slow that heat dissipation? My hypothesis is that it primarily was driven by these clear cold nights, diurnal recrystallization, but that there was definitely some effect from this residual heat. I've got just one slide on preservation, and then I'll be done. This is another great figure from Jameson that shows how long different weak layers persist in the snowpack until they cause avalanches on those layers. And you can see precipitation particles decomposing faceted are fairly short-lived. Surface hoars can be up to a few weeks. Faceted crystals and depth hoar can be very long-lived in the snowpack. This is from 70 snow profiles over 14 years. In our events, obviously this one, are way off the chart for this study, which was looking at how persistent weak layers can be. So this was a very persistent weak layer. And really, all three of these bullet points just say, what I kind of came to discover was, one reason the facets stayed so long is they were just developed so well. Once you have very well-developed facets in the snowpack, they tend to just stay there. Settlement is slow because they have high strength and compression. There's probably some upper bounds on the density that you can compress these to. And this idea from Kolbeck of self-sustaining facets, which I won't get too into, but they tend to just sustain themselves in the snowpack. And last, we had this rain crust. So this was obviously a big influence as well. It wasn't just this faceted layer in the snowpack. And I think the rain crust really helped in two ways. It prevented these layers from bonding because of this big grain size difference, facets sitting on ice. It's really hard to compress those facets and have them bond into the snowpack below. And then we had that crust there. So, and Kevin Hammonds is one of our speakers. He's shown some great work about near crust faceting, which was certainly happening probably all winter, and also preventing bonding of those facets. So, with a rain on snow event like we had, one of my take-home messages is the details really matter. The timing for the freezing of the rain and when you get your new snow on top of that rain event is really important on the scale of hours to days. And it's possible that in our situation last year that this latent heat and the residual heat from the rain affected the temperature profile even many days after. So the idea is that you can have a hard frozen rain crust, but it's not cooled off. It still has a lot of heat from that rain event in it. So it kind of, in my mind, amplifies that diurnal recrystallization process even a little more. And ultimately, a lot of what I'm saying, when you're assessing avalanche hazard and out traveling the mountains, this is fun stuff to talk about over beers and whatnot, but these are the two big equations, right? And that was our situation last winter. And having that crust was a sliding surface as well, which I haven't even mentioned. But, and one last thought to mention that this could become more common in the future as we have rain events in the late fall, mid-season thaws, and putting these sorts of crusts into the snowpack. So, and this was definitely a collaborative thinking effort. So if I've used your snow profile and your photographs, and if I've talked with you about this, thanks very much. It was definitely a mutual project.